Before time has its name, the first master of all elements, Tim Chemistry, started creating things using 118 elements. But Tim realized that he can only make 118 things with 118 elements, and that means the air fryer wouldn't exist. So, after 40,000 years, Tim decided to play a four-dimensional move. He bonded elements together using their electrons. And that's how chemical bonding was created. After a few videos talking about how electrons function around the nucleus, now we will talk about how electrons bond elements together. First things first, we have to understand that everything in chemistry revolves around the rule of stability and efficiency. Why does an electron do this? Why does this element tend to bond with that element? It's because it's more stable than other methods. Look into the periodic table. There exist noble gases, which have all their orbitals maxed out with electrons. They're called stable. They need not more electrons to cover their orbitals, and their electron configuration are the goal for every element prior. But to just simply change electron configuration will result in the change of element, and that is of course difficult. Elements instead take on a simpler approach, borrowing or giving electrons away. That give-receive action creates chemical or ion bonding. We will take the most generic compound as an example for this type of bonding, salt. So, sodium, with its configuration being neon 3s1, either 7 electrons short or 1 electron spare from being a noble configuration. Another element in the compound, chlorine, has a configuration of neon 3s2 3p5, either 1 electron short or 7 spare electrons from being a noble configuration. The most effective option for these two elements is that sodium should give away its 1 electron and chlorine should receive the given electron. So sodium turns into sodium plus cation and chlorine becomes chlorine minus anion, both having a neon and argon configuration respectively. Side note, the duet rule and the octet rule is basically the noble gas configuration rule but for S&P orbitals. Anyways, a cation is an element that donates electron. An anion is an element that receives electron. So sodium plus is a cation and chlorine minus is an anion. Now, is there a pattern for when an element gives or receives electron? Of course not. Just like how xenon, despite being a noble gas, still gives out its stable electrons like nothing. Determining when will they give or receive is probably impossible. We could, like how we predict where electrons appear somewhere, guess which type elements will give or receive electron. So, elements in groups like 1a and 2a tend to give, and 6a along with 7a tend to receive. Okay, bonding behavior aside, there are currently 3 ways to demonstrate the bond between elements, which are electron bonds, Lewis bonds, and structure bonds. Let's give a brief description about each of these bonds. Each way to demonstrate bonding is some part less detailed than the one before it. So, for electron bonds, they have dots that represents electrons. These dots, of course, surround the atom. However, you need not dot out every electron of an atom, but just the outermost shell. Take once again salt. For example, sodium has 1 outermost electrons, so 1 dot around the atom. Chlorine has 7, so 7 dots. Connecting them, we get this, in which the 2 dots in the middle represents the bond. Double bonds will have 4 and triple bonds will have 6 dots. Next one, the Lewis bond, which only change how the bonding is demonstrated. Turn the 2 dots into a dash. For single bonds, 1 dash, double, 2 dash, triple, 3 dashes. One thing you could do to gain a few millisecond time advantage is to change 2 electrons next to each other into a dash. And finally, structure bonds, which is just dashes all the way without showing any orbiting electrons. We will use Lewis bond since it's a named bond and it's also the fusion between electron and structure bond. Alright, let's have some examples for this. First, we have CH4 and CO2. To explain the bonding between these elements, we have to draw the outermost electron cells for carbon, hydrogen, and oxygen. Methane first. We can see that carbon has a pair of electrons in 2s and two singles in 2p. As for hydrogen, there's just one s. Unlike the kind of homeless hydrogen with just electron, carbon has four electrons alongside with an empty xz orbital. Not to show disrespect to hydrogen, it would excite an electron in the 2s pair to jump to the empty orbital. These singles would then share their shell with four electrons from four hydrogen atoms, creating methane and the CH bond. Showing this in the Lewis bond, we have carbon as the central atom, four dashes surrounding it, and at the end of each dash is a hydrogen atom. For carbon, each dash surrounding it represents a pair, so four pairs make 8 electrons, approving the noble gas or octet rule. For hydrogen, surrounding it is just a singular dash, 2 electrons, once again, approving the noble gas or the duet rule. Now, why would carbon excite its electron in order to create methane? For one, CH bonds are very, very stable. Another reason is also mentioned above. It has an NT orbital. And also because singles per orbital is better than pairs in orbitals, as we have known from the previous videos. Now for CO2, we know that oxygen is clearly not broke like hydrogen. It is, in fact, 2 electrons richer than carbon. But when we look at the electron cell for oxygen, it has no empty orbital, thus no reason for it to excite its electrons. So once again, carbon would have to do it. Each oxygen atom with two singles attaches them to two singles from carbon. This creates the double bond. To perform this in Lewis bonds, carbon as the central again with four parallel dashes, each two connected to an oxygen atom. With four dashes surrounding the atom, carbon has 8 full electrons. Oxygen has four dashes, two connecting to carbon, another two are from the 2s2 orbital, and a pair in the 2px orbital. Both carbon and oxygen have 8 electrons. Both of them are in noble gas configuration, and so two stable atoms create a stable compound. One thing that you may or may not have noticed, all elements in the example are under period 3. But when you move on to period 3 and above, there will be a lot of exceptions. For example, SO2. For sulfur, the outermost shell is 3s2 and 3p4, so it has two unpaired electrons. Here's how the exception comes into play. Each of the two oxygens miss 2 electrons to have a noble configuration. So two things can happen. One oxygen will have 1 electron demote from Pz back to Py, while sulfur will add two singles to the other oxygen and add its pair in Px into the empty Pz shell in the aforementioned oxygen. This makes all elements have 8 full electrons, following the octet rule and the noble configuration rule. The second option is for sulfur to promote 1 electron in a pair in the px orbital to a single in its 3d1 orbital. Now, each oxygen will receive two singles. This makes two double bonds, at the cost of sulfur having 10 electrons instead of 8. If you haven't guessed it yet, the second is more stable and is the correct structure. Don't take my word for it, but sandwiched by two double bond is apparently more stable than having a single and a double bond attached. What's taken from this is that period 3 elements above tend to excite their electrons to make singles in order to make bonds, whilst the first two tend to donate and receive electrons. Right, now that we know how to make Lewis structures, we could determine something called formal charge. A formal charge of an atom is basically a way to determine the stability of a structure and also its charge if it's an ion. The closer the formal charge is to 0, the more stable it is. What you first want to do to determine formal charge is to draw the compound's Lewis structure. After that, you want to see how many electrons completely belong to an element in that compound. Then, you take the initial amount of electron of that element and calculate the electron difference. Let's visualize with an example. We will take the cyanide ion. The cyanide ion, after drawing its Lewis structure, we get a triple bond and two pairs for both nitrogen and carbon. So, nitrogen, the element initially has 5 electrons in its outermost. Now, instead of considering the triple bond as 6 electrons that belongs to nitrogen, we only take half of it, which is 3. Then we add the amount with a spare pair. We get 5. The difference between the initial and the Lewis is 0. Now for carbon, we once again take the triple bond and split it. Then add that 3 with carbon's own pair, we get 5. We can see that the Lewis has one spare electron compared to the initial, hence the carbon has a -1 charge. Adding both the formal charge of the elements, we get -1, which is also the charge of cyanide. Okay, time to tell you how to draw Lewis structures for most cases. First, we calculate the sum of all outermost electrons in the compounds, including elements that appear more than once. Then, we connect all elements with a single bond first. After that, we fill in each element until they have 8 electrons, and then we start filling the core element. The core element is usually the element with the most electrons. Next, we calculate the absolute value of the formal charge for each element, sum them up, and take the absolute value. And finally, we could lessen it down by turning electron pairs into bonds. So for example, iodine 3, each iodine has 7 outermost electrons, and it's iodine 3 minus, so that's 7 times 3 plus 1 equals 22. Next, we connect 3 iodines together, and the middle will be our core element. So for each of the 2 iodines on the side, they will have 6 additional electrons to make 8. We take 22 minus 16 and we get 6 for the last iodine. Now we calculate the formal charge for each iodine atom. Each of these side iodines have 0, but the core iodine has a spare, so its charge is -1, which perfectly fits the atom. One thing regarding two Lewis bonds is that they also have resonance structures, which are structures that have elements with different bonding, yet hold similar stability. So for example, the thiocyanate ion, the total amount of electrons is 12. After drawing single bonds and giving 6 electrons for both sulfur and nitrogen, we have the formal charge for sulfur, carbon, and nitrogen are -1, +2, and -2, respectively. Now we have two options. We make a triple bond with carbon and nitrogen, which makes both elements have 0 formal charge while leaving sulfur with a 1- charge, or have carbon sandwiched by 2 double bonds, which make nitrogen have a charge of 1-, while the rest have 0 charge. Both are equally stable, so they are resonance structures. Let's have some examples to familiarize with these theories. Pause if you want to do it by your own. If not, here's the solution. Right, for hydrogen sulfide, it should be pretty obvious that it follows octet. For phosphorus trichloride, we have phosphor as the core element with a single bond attached to each chlorine. All 8 elements have 8 electrons, so this follows octet. For xenon dioxide, the core xenon will excite its pairs into singles in its d orbital in order to create 2 double bonds for each oxygen. All have 8 electrons, so this follows octet. For phosphorus oxide chloride, we have phosphorus at the core followed by 3 single bonds, each for a chlorine and a double for the oxygen. This has 8 for each element, so it follows octet. Now for thionyl chloride, the core sulfur has a double bond with oxygen and 2 singles attached to a chlorine. However, the sulfur also have a spare pair, which makes 10 instead of 8, so this does not follow the octet rule. For this exercise, we must note that for acids, hydrogen most likely bond with oxygen instead of the core element, since oxygen will most likely have spare electrons to bond. So, for phosphoric acid, 3 OH groups connected to phosphor and 1 oxygen with the double bond connected to it. The formal charge for all elements is 0. For sulfuric acid, sulfur is connected to 2 OH group and connected to 2 oxygen by double bonds. All formal charges are 0. For chloric acid, chlorine is connected to an OH group and connected to 3 oxygen via double bonds. All formal charges are 0. Now, nitric acid is a bit different from the rest. Nitrogen is a period 2 element and it only has 5 electrons, which means it doesn't have spare electrons like those period 3 elements to excite. So, nitrogen has 1 oxygen connected to it via double bond and an OH group also connected to it. The remaining oxygen, however, will only connect to it using a single bond. Calculating the formal charge for all this leaves us with nitrogen having 1 spare and oxygen having 1 less. Adding them up makes the compound 0 charge. This is the end of the first video in chapter 2. Next video, we will discuss about orbital overlap and the VSEPR.